Hello? Hello? This question is for the two people who joined. Can you hear me? Okay, so the volume seems to be working out fine. I've got one of the TAs to confirm that we will be starting in 5 minutes. And I have Piazza open and I have this YouTube chat window open. So in case you guys have any questions, you can type there. All right, so hi guys. We should be starting with the session now. It's 8:02. Or maybe we can wait for, okay, people are still joining. Maybe we can wait for 3 more minutes and we'll start at 8:05. Um, I wish I could see you guys too, because this just feels like I'm talking to, I don't know, not even myself. Uh, that's Tad, by the way. All right, let's start. Let's not penalize the people who are on time. So this assignment is on k-means and on clustering, basically k-means and Gaussian mixture models. It will help you if you guys have the assignment downloaded and if you have the README in front of you and em.pdf and the assignment folder itself. Let me see. Yep. Again, I will be monitoring the YouTube chat windows off and on, and also Piazzas in case if you have any questions, you can type in there. Um, okay, see. So unsupervised learning, as you guys would have gone through the lectures in the Udacity, and Thad talks about unsupervised learning in his lectures. Um, it is when you have a lot of data points and you don't have labels in front of those data points. Um, so it's just a logical extension of supervised learning, in the sense that what would you do if you know that there could be some sort of pattern in the data but you don't have the labels for them. So you try to find similarities amongst individual data points and try to group them together. The grouping them together is clustering. And if you want to go into more details, I won't go into more details of the entire unsupervised method and everything, because that's still there in the lectures. I'll stick to k-means and Gaussian mixture models, which are specific to this particular assignment. Um, as an example, before moving on to the specifics of how to implement k-means and how to go about implementing Gaussian mixture models, I would want you guys to have a look at the input folder, at the assignment 5 folder that you've got. And I guess now is a good time to start the screen share. Okay. How do I do this? Screen share. Can you guys see the screen right now? Can you guys see images folder? This is the image that you have. And for example, this. Well, I could have done this before. All right. Well, I guess you can see the screen share. So, before moving on to specifics of K-means and EM and Gaussian mixture models, you should be able to see the four images. You have all these images in your assignment folder itself, assignment folder as well. But I wanted to highlight that this is what you are aiming at in this assignment. This is what you're aiming for in this assignment. Um, this is the original image that you have. I think it's a great example for depicting clustering because even after clustering, you can actually identify that the image is that of a bird. Uh, the whole idea of clustering an image, in fact, it is so prevalent that these days you won't find it. You won't actually have to code it. It's already there in a lot of libraries, and it's more of a pre-processing step these days rather than an end goal. Um, but we still want you guys to implement it because it solidifies the basics. So if you see the image here, which is just these two colors, it's basically when you're clustering this entire image in two clusters. You're saying that I just want two clusters out of this image. What is happening here is that every pixel in the backend, what the clustering algorithm is doing, that in every pixel is being allotted to one of the two clusters. These colors that are given here are not random colors. This is the mean of um, this is the mean of all the color of the color of all the pixels which are there in that particular cluster. And on what basis do you assign these clusters? Again, K-means and Gaussian mixture model is one of the are two of the algorithms, but these are the outputs of your k-means algorithm. If you run your k-means, a properly implemented k-means on this perfectly fine, beautiful, colorful image of this bird, and if you say that I want to split into two clusters, I want the uh, k equals to 2 or 3 or 4. These are the images that you should get. Uh, what is happening here is again, like you said, if you increase the number of clusters from 2 to 3 to 4, you can see more colors coming up. Again, these are not random colors. These are the average of of the colors of all the pixels that are coming to that particular cluster. I think this should give you an idea of what the clustering would be doing. So let's go on to the assignment itself. This is the folder that you'll be having, em.pdf. We'll be referring to it in the session itself, and also you will have to heavily use it. I will highlight the important sections of this particular PDF, which will help you implement the particular parts, part 2, part 3 of the assignment. Helper functions.py is what you're supposed to submit. This is extra. This is because I ran the code, so usually you're not supposed to have this. Sorry, helper functions.py is the contain all the helper functions, which are also very important. We should be going through these as well because you will be heavily using the helper functions that we provided. Images, feel free to look around, see what is there. Party Spark and bird images. These are the images that you have with you to test on. But be mindful of the fact that on Bonnie, we have different images to test your code on. So in case you somehow get the final solutions and you think that submitting it work, that won't happen. Mixture models.py is what you're supposed to submit after filling it up. Mixture test is the local test that we have provided. Uh, Make sure you're passing all these local tests before submitting to Bonnie because you have only 5 submissions. I want to highlight you have only 5 submissions for this assignment, and because of that, we'll be taking your best score. README, we'll be going through the README anyway, step by step, and rest all is the usual stuff. So let's go on to see the README, creating due dates, submissions, all of this. Again, 5 submissions per submission will be used for the assignment. Um, Resources. Other than this, you're allowed to look up online and read more on Gaussian mixture models and k-means. If you feel you need more help, you can obviously come to the office hours, and the TAs will be more than willing to help. This is where the important part starts. Let us first go to K-means. Okay, so K-means is a type of hard clustering method. By hard clustering, I mean that you will be allotting every point to exactly one cluster, which is usually decided by the closeness to that particular cluster. And how do you compare closeness? How do you calculate this closeness? You calculate the distance between that particular pixel for which you are trying to make a decision for, and the distance of that particular pixel with the means of all other clusters. K-means is an iterative process. Clustering entire it's an iterative process. Gaussian mixture models will be an iterative process. What you do in K-means is you arbitrarily start with um, one. You have to decide how many clusters you want, and for example, you want K clusters. You will be randomly picking up K numbers as the initial means. Second step would be to calculate the distance of all the points in the image with this with these means, with all of these means, and allot every point to the particular cluster, to the cluster for which its distance is minimum. Uh, Once you have all the points allotted to all the points allotted to specific clusters, and make sure you have to allot every point to a single cluster. So at the end of this one iteration, and the iteration is also not complete, at the end of this distance calculation and allotting points to allotting on the clusters, you will have individual clusters where for which you know that these certain number of points belong to this particular cluster. Now you can recompute the mean, and the means, of course, I mean, because you started off with random means, your means are going to shift. They might significantly shift, and that's the whole point. You keep doing on this process iteratively again and again and again until your means decide to not move at all. I think we have given you the specific convergence condition. Your convergence test should be whether the assigned clusters stop changing. The assigned clusters stop changing means your means are static after that. Note that this convergence test is rather slow, and yes, it will take time. When no initial cluster means are provided, it should choose k random points from the data, and that's how you start any clustering process. Without replacement, why do we highlight without replacement here? Because you want different means for all the clusters. You don't want two clusters to be having the same means, which will be basically a single cluster itself. Because here you are identifying clusters from their means, like how what are the parameters of what are the parameters associated with a cluster? How do you define a cluster? Here it's just means, like every cluster will have its own means, and that is how k clusters k means, and that is why it's called a k means clustering process. um, this is very important. Try to vectorize your code. Look up for sources online for vectorization, and we have given hints here, but NumPy will be your help. Go through NumPy should almost always have functions for um, doing things without a for loop. What we do want to highlight here is because a lot of students have they fall into this trap um, of numpy.vectorize, because it seems by the word that it's going to vectorize, but it doesn't. It just forms a loop. Are there any questions regarding k-means before I move on to Gaussian mixture models? Let me first the okay, it doesn't look like. Okay, this is the more important part, and I'd say it's less intuitive, but it's also it's more logical as compared to a hard clustering method that is k-means. So Gaussian mixture models is a soft clustering method. What do we mean by soft clustering? By soft clustering, we mean that every point is not allotted to just one cluster. We calculate the probability of that point belonging to all the clusters. We calculate its probability belonging to all points, um, belonging to all the clusters, and this is done for all the points. So, and that is how you arrive at something called likelihood of the trained model. Um, as you see, these are the functions that you're supposed to implement. The reason that we've said that it'll be helpful to implement the functions in this order is one, because that's the order in which they are being tested, and also because that'll help you understand um, understand things easier. Because I guess these are not the order in which it is mentioned in the mixture models .py file. Initialized training is where you will initialize all your mean, standard deviations, and mixing coefficients. So the difference here is that while in k-means, you're this is, I guess, the point where I should switch to the mixture models. Yes, the file itself. So you see, in k-means, it was just the clusters were identified by just the means of their clusters. Then that was enough for the entire algorithm to perform. In Gaussian mixture models, however, every cluster is identified by three parameters, which is your means, your variances, and mixing coefficients. Um, Means, as the name suggests, variances, again, as the name suggests, mixing coefficients is to give you an intuition. Uh, it's um, go. It's basically in what proportion are these clusters that have been identified, in what proportion do they mix together to give the image that you have. Correct. So that is why it's important to implement initialized training first, because here is where you'll be giving valid values to variances and mixing coefficients and means. You'll be initializing all the variance to one, you'll be initializing mixing coefficients to basically all the mixing coefficients will be initialized to 1 divided by the number of components. And why is that so? Because at the beginning, you don't know which cluster is more important, which cluster is less important. Once that is done, you go about implementing joint probability. This is of a particular value. So also from here on, from Gaussian mixture models, you will be doing only grayscale images and not colored images, which was what you were using in k-means. So when you're calculating this joint, what does it mean? What is the meaning of this particular function? That is, for a given pixel value, you are basically calculating its the log. Remember, you have to return the log joint probability. So remember to return the log of that function, the log of that particular value. So you are returning the log joint probability of a particular point belonging to all the clusters. So basically, um, you'll be given a value, you'll be given a grayscale value here instead of this entire a three-dimensional, not three-dimensional, but instead of an RGB value. That should give you a joint probability. The next step, as mentioned in the README, the reason why I mentioned after initialized training joint probability likelihood is because you you calculate the probability that the joint probability that you calculate in the joint probability section for one pixel. Likelihood is just summing of all those probabilities for all the pixels. Likelihood is what you will calculate after every trained for a particular trained model. That is to say, once you complete one iteration of Gaussian mixture models, once you have um, allotted every point to you have certain probability of every point belonging to each cluster, and you have that is what your trained model of that is what your trained Gaussian mixture model would be like. After each of these iterations, you'll be calculating likelihood of that particular model, how good it can be intuitively thought of as goodness of the model. And the formulas for this, I'll go into the formulas for all of these. So that is why once you calculate the joint probability, you're doing it for one point, likelihood, you're doing it for all the points, which will also give you a sense of goodness of the model. And next, you start with implementing the train model. This is where you actually go through all the iterations of the expectation max of Gaussian mixture models. This is your EM algorithm. Um, Here is where your em.pdf will be useful, and I will come back to that. Segment is once you have trained the model again after an iteration, you will want to know, because you have to produce an image. You have to remember k-means. You saw those parrot image or the bird image. I don't know if it's parrot or not, but the bird image where you have k equal to k equals to 3, k equals to 4 clustering. Um, to produce a similar effect, you will allot every point to a cluster uh, based on the maximum probability of that point in based on the cluster in which it has maximum probability of going. These probabilities will of course change after every iteration, but that is how you segment the image, and that is how you will calculate the best segment. But that's for later. I want to stop here and move on to the README, because all these formulas, joint probability, likelihood, and train model, will require you to use these formulas. This is exactly the formula that we're using for joint probability. Make sure that we have asked for log joint probability, so you'll have to apply log in front of these equations. We expect you to do all the calculations in log space. That is to say, if you come across any equation which is not in log space, apply log, use the formulas of log a by b equals to log a minus log b, and similarly perform all the calculations. Um, like you say, if you want to, if you see here the formula for this is the joint probability formula that you'll be using in that particular function. If you apply log, you will split these terms into log of mixing coefficients and log of um, ni, which is basically just the ith Gaussian distribution underlying the value x with mean mu and variance I. So basically, it's x, that is the point for which you're calculating, the probability of that point belonging to a cluster um, which is characterized by mu I, that is the mean, and sigma I, the sigma I square, that is the variance. Now, if you want to know what the log of this particular term would be like, this is given here. So rest assured, we've given you all the particular all the formulas that you'll be needing in the assignment. This is the log from the Gaussian probability, as it says, and this is exactly the same term as you saw here, but after you applied log to it. So make sure when you're doing calculations in log space and when you're converting it back to exponentials, please be very careful of that. This is where most people make mistakes. So this will give you the probability for this will give you the formula for joint probability. That is one of the requirements in basically this. Initialized training is just setting your variances to 1, means random, and coefficients equal. Joint probability is the formula that we just saw above. Likelihood is the sum of that for all the points. Train model is where you'll be training your EM. This is the second step here. Use EM to train the model to represent image as a mixture of Gaussians. Please refer to the EM document again, sis. We'll go to this right now as the next step. To initialize EM, set each component need to grayscale value. We've already done that in the initialize training step. No, there are packages to run EM automatically, but please implement your own version because that's what we want you to do. We have set the convergence condition for you in Gaussian mixture model or default convergence. So as of now, until this point in the assignment, you do not need to worry about the convergence condition. Let us go to em.pdf. Wait, I have a couple of questions here. Can you explain in terms of image pixels? Um, Karthik, could you elaborate what you mean by explain in terms of image pixels? And I will explain EM and I can come back to your question. Rupal, I'll be going through em.pdf right now. So I would recommend reading the entire document because it helps. It helps to set the um, it helps you to understand what K means, what EM algorithms, and what Gaussian mixture models are. But the part that you have to implement for that, the formulas that you need are right here. Now, they have given you in terms of expectation step and maximization step. That is what you have. You will have one EM step and one iteration. And again, we've given you the convergent condition. I will, I mean, you can trust these formulas blindly, but I will try to give you an intuition for all these formulas. Let us start with the first step. Also, note here we have, in addition to means, variances, and mixing coefficients, we have something called the responsibilities. What a responsibility matrix is, it's basically, think of it as your columns being your clusters, your rows being all the points that you have in your image. Um, the responsibility matrix is basically an I comma j in the responsibility matrix, a row comma column, a particular cell would mean that this particular pixel's contribution in a given cluster. So the ith pixel contribution in jth cluster. Um, I guess this was one of the questions that Karthik had. Can you explain in terms of image pixels? When you say, when I say ith pixel, if you look at a 2D image, it can be difficult to understand. If you consider a 2D image, it can be difficult to understand what you mean by an ith pixel, uh, which is why we have highlighted in the README that you should use flattened image matrix and unflattened image matrix liberally, like heavily. You will be needing them. These are helper functions that we have provided. This is way of helper functions that we've provided you. Um, your flattened, so for a 2D image, and why I'm saying 2D is because for Gaussian mixture models, you're working with grayscale images. For a grayscale image, which will be 2D, a flattened image matrix would just place all the columns next to each other. So you will get a 1D matrix out of it. On that 1D matrix, if you try to calculate these responsibilities that I just mentioned, on that 1D matrix, you will have all the points in I, for example, as a row, and columns will be the number of clusters, all the clusters that you have. Responsibility, giving intuition of responsibilities. Responsibilities would be the share of each pixel in each cluster. So if this is the responsibility matrix, the way they have the way that I described, um, the sum along the rows should be 1 because a particular pixel's contribution to all summing a particular pixel's contribution to all the clusters should be 1, and along the column you have along the column it would not be 1. You'll see what I mean. So the expectation step, second step is the actual expectation step, where you're saying you're supposed to evaluate the responsibilities of the current parameter values. This is the term that they're using for responsibilities. N comma k is nth pixel and kth cluster. Pi k are the mixing coefficients. N, xn given mu and covariance is the same formula that we just saw in the README, which is exactly this, which is again the log probability of uh, the log form of the Gaussian probability. That is the probability of a point belonging to a cluster with mean mu k that belongs to the kth cluster, which you represent here with mean and covariance. And yeah, the denominator here is because we're calculating responsibility, and if you think about it, the way I described what responsibilities are, the denominator is just the sum of all those values, and that is how you'll get a probability, a value which is between 0 and 1. The next step is to re-estimate the parameters, and the parameters, like we initially discussed, it was means, variances, and mixing coefficients. Means are, okay, this again is the responsibility. It can get the reason I'm going through all of this is that it can get a little difficult to understand what these different symbols mean and everything. So I want to go through what these formulas are exactly. This entire term represents a responsibility for nth pixel in the kth cluster. Um, Again, we since we are re-estimating the mean here, so we'll be looking at all the pixels which will. Okay, I was about to say we'll be looking at all the pixels which belong to this particular cluster, but remember this is a soft clustering method. So it is not like k-means that you'll have just specific points belonging to one particular cluster. You will have all the points contribute to all particular cluster in different ratios. This is which is where your responsibilities are going to help, because the responsibility is exactly that probability of a point belonging to a particular cluster. This is the absolute value, absolute grayscale value of that pixel, and you sum it over by like mean, like an absolute mean, not mean here. It would have been just to divide by the total number of points. But here, since the total number of points are not exactly like here, this nk does not represent the total number of points. It's something similar to it, because while all the points contribute to a particular cluster, they do not contribute in the same proportion. And nk takes care of that. It is basically just sum of all those responsibilities for that particular cluster. Sum of all the points, some of the responsibilities of all the points, but for the given cluster. Intuitively, it should tell you that it's dividing by all the points in a cluster, but it's not exactly that. I hope I'm making sense, because it is difficult to understand why these formulas make sense. You can, of course, straight away just implement them and get them to work, but it helps if you understand what you're doing and why you're doing that. Wait, let me see if I have. Okay. This is how you calculate means. In a similar way, you'll be calculating the covariances. Again, you see the denominator is the same. You still have the responsibilities, and why we are subtracting every point from the mean, because that is how you calculate covariance in outside of this environment as well. It's just a standard formula. Again, these are your new mixing coefficients, and it's a pretty straightforward formula. If you get an idea of what mixing coefficients are, if you get an idea of what responsibilities are, all these things should start making more sense. We have discussed what NK is, and the next step is to evaluate the log likelihood. Because again, the log likelihood is the way of saying how good is my current model, how good is my current clustering. This formula is again the same formula that you have been doing all this while here. So if you find this easier, you can pick up from here. Nine. Let's say Nikhil says, can you review 9.25 in detail? Yes, but beyond that, okay. So this again, gamma, Z, and K is just responsibilities, which is similar to saying that responsibility of point n in cluster K. Since you're taking care of only kth cluster, you'll be looking for responsibilities in that particular column. If we have the responsibility matrix as I just described, that kth column represents one particular column represents a particular cluster. This is just is probably highlighted, but this entire thing is calculation of covariance in general, which is xn is the absolute value of the point that you're looking at, and mu. Remember, this is the new mu you just calculated in this step. You'll be subtracting with you'll be subtracting every point. Uh, you'll be subtracting the mean of that particular cluster from every point. Uh, it won't be, as a hint, what I can say is that it won't be an exact this won't be exactly how you'd be using it, because now you have a 1D matrix. Beyond that, there will be implementation details which I am not supposed to go into. We are supposed to let the students figure out themselves how to exactly use the formula. But please give it a shot, and if you are not able to get to the solution will be more than willing to help you through Piazza and other stuff. Does it help, Nikhil? Does it make it any clearer? Xn is still X and mu are still the absolute values and means, and gamma is the responsibilities. Evaluate the likelihood, and this is just one iteration. The entire thing is EM that you just say is just one iteration. You need to keep doing it until you reach convergence. You have to check for convergence at every point. And we have, yes, that is a transpose at the end. Nikhil asks, is that a transpose in the end? It is. Um, let me see. There's, yeah. So the the steps that we discussed for EM, all of it will go within this train model. We have given you a default convergence check. It basically checks for the change that you have in the log likelihood for 10 consecutive iterations. If it's within 10%, then it says that it has converged. This is default convergence, train model, segment. Now that you have trained your model using the train model, segment the image matrix into pre-specified number of components. Um, feel free to use, feel free to save the image matrix that you get um, as an image and visualize it. Helper functions have image to matrix, they have matrix to image, which you can use to visualize your image. Flatten image matrix is what I've been talking about so far. Um, Converting a 2D image into 1D and using it from there on, using NumPy matrices from there on. Unflattened image is if you want to go back from this 1D image to 2D image. Again, it is not necessarily just for 2D to 1D. It'll work for it'll work for RGB images as well. It won't just work for grayscale, it'll work for RGB images as well. Flatten image from height by width by depth will be, but it'll be converted from 3D to 2D, and uh, that should be a lot of help for you. And flatten image differences. This is mostly for us. You probably don't need to use image differences. Okay. Uh, So segment is when you allot every point to a particular cluster so as to visualize, and that is how you find clusters would be. It is basically nothing but you'll allot a point based on its maximum probability. Based on its probability in all the clusters, you'll pick up the cluster in which it has maximum probability. Likelihood, which is discussed. Best segment is again, since um, since you're training starting off from random means and expectation maximize and this Gaussian mixture models need not necessarily take you to a global optima. So we suggest that you run the entire training. You train basically, say, 10 different models, which would be determined by the number of iterations till convergence. So by training 10 different models, I mean take every model till convergence, get the likelihood of that model, and if the new likelihood is better than the ones that you already have, you save the new model. Otherwise, you can discard the new model. This is just a way to get to closest to the global optimum. And this is where your part two of the assignment ends. That is implementing a Gaussian mixture model. We have covered log likelihood, segment by segment, in this particular order. You can do it in any order, but this will help you with the understanding. Couple of things that I do want to highlight, and I have already highlighted in the README, but still, this is very important. Please, I mean, it seems that yeah, it's easy to do. It's doable. You can do all the calculations in log space, but remember of the conversions when you're going back and forth into log space, because this is where most people make mistakes. Here's the mean, sigma is the standard deviation. We've talked log sum x is a very important um, function that you will be using when you're going back and forth. We have already given you the inputs in NumPy arrays. It will help you to do all your calculations in NumPy arrays. You will need to vectorize your code as we've highlighted again and again. And this is the part where we've covered all these parts. The third part is model experimentation, which is basically improving the current Gaussian mixture model that you have. The first improvement is initialization itself, because right now we're just taking random means. Um, I cannot straight away point to the answer for this, as in which method of im, which method you should use for improving the initialization. But clustering is just one of the common methods. Cannot go into much details here because this is just improving upon the existing code that you have. Convergence condition, this is where you'll deviate from the default convergence function. This is where you'll implement your own convergence function, which is the difference would be it's still same in terms of we're still looking at 10 consecutive iterations, and we're still looking that the new values should be within 10% of the previous variables. But instead of using log likelihood as the value, we will be as in we ask you to make sure that all the three parameters for a particular cluster, for in fact for all the clusters, means, variances, and mixing coefficients, they are within 10% of their previous values. This maintained for 10 consecutive iterations, and you say that it has converged. And this is the part three. That's it. That's pretty much it. Implementation wise, in mixture models, we have defined a new class itself. So you will have to change your train model a bit um, just to include the new convergence condition. This is what you'll be filling. Initialized training is pretty much the same as the previous initialized training. You can copy paste from the previous part. If you do not want to, if you are just doing the convergence function, if you want to change, then you will have to implement your own way of initializing it better than just randomly picking up the means. Gaussian mixture model convergence is what will be testing your new convergence function. This is pretty much the only difference here. If you see, we're passing the new convergence function. In the previous class, we were passing the default convergence function. The Bayes info criterion. Wait, I'll pause here to see the questions as of now. The T represents the transpose. So a couple of questions here regarding equation 9.25 in em.pdf, that you have a T at the end which just represents a transpose. That is how you calculate covariance when you are dealing with 2D matrices. You'll probably not need to. You won't be needing to do that most probably, but from here on, you have to figure it out on your own. Sorry, can't help you beyond that. Any other questions regarding the three parts that we have discussed so far? Because these are the most important stuff, especially part one and part two. Part three, if you have gotten as far as part one and part three is just minor improvements on top of it and minor changes. Let's check Piazza as well. So there are no questions on Piazza and no questions here. Okay, so I will continue with part four of the assignment, which is patient information criterion. Uh, this is a very specific, this is a new concept. This is probably not covered in lectures, actually. Even Gaussian lectures are not covered in lectures in so much details. But the idea here is that we are trying to maximize the likelihood, the log likelihood of the models that we get. The best cluster that you could get is if every point is its own cluster, but obviously you don't want that. So patient information criteria is what it's a big, basically, in short. You calculate, instead of log likelihood, you calculate the big model test and big likelihoods. Those are the questions that you have. You calculate this patient info criteria, BIC, for the trained models. And what it does is it penalizes the number of clusters that you have so that you don't end up in a situation where you have every cluster for every point. So it's sort of trying to strike a balance between good clustering and also the number of clusters. It is a pretty straightforward function. It is a pretty straightforward formula, and you should be. We've given you the link to the Wikipedia article for that. You are free to read the entire thing or pick up the main part, get the gist of what BIC is and how to use it. Again, remember that the formula for BIC depends on the number of components, the total number of free parameters, and we have mean variance and mixing coefficients. There is three different components for each cluster. So you'll have to calculate your free parameters accordingly. For A is pretty much just using the formula on Wikipedia and turning and writing it into code. For B is testing your model, which is we have just given you the initial means to start with. You can uncomment this code and see how well you do. Ideally, it should be able to start with k equals to 2, k equals to 3, k equals to 4. All these, it should perform all these clustering methods, and you should pick up the one which gives you the best value for BIC, which is what we ask you for here. Choose the best number of components based on all these. Uh, you are just supposed to return what you got as a result of the previous function. That is this. The bit likelihood question, you're supposed to change these values and replace it with the number of clusters that you found the best based on this particular function. Big likelihood model test. Return your name is pretty much straightforward. We do that for all the assignments. I am not supposed to go into the bonus, but I mean, of course, not the bonus implementation. But if you are attempting the bonus, please remember that memory can be an issue. We initially used to say that you have 500 MB of memory, but the Bonnie overhead itself takes up to around 200 to 250 MB. So this time we have restricted it to not more than 250. I mean, you should be able to find a solution to this which runs within the given time and does not overshoot memory expectations as well. Can now go to specific questions. JP Robbins says, what does a component mean in EM? I'm assuming it is not the same as parameters for the models. No, it's not. The parameters for the models is the three parameters. For the wait, do you mean for the model or for a particular cluster? And I will go back to user provided train the models, then fill out bit likelihood questions to return the number of components in both main big and maximum likelihood model. The components here means the number of clusters. Can you talk about the likelihood function and expectation equations again? Any specific equation? Any specific? Do you mean em.pdf or do you mean the equations from the README? So the question is, can you talk about the likelihood function and the expectation equations again? Is it the likelihood function in uh, the max likelihood function that we're asking for in the assignment and the entire em.pdf? Because that'll be just repeating whatever I talked about in part 2 description. Both. Okay. See. Okay, so I will start with the readme this time. If we start with this particular formula that you see here, it says joint probability fx, where x is the grayscale value. So it's basically the joint probability of x belonging to all the clusters. That is, mi is your mixing coefficient. This entire term, that is ni x given mu and sigma square, just means that the probability of n is your probability distribution function. I'm sorry if I haven't mentioned that. Uh, so this entire term means the probability of the given grayscale value, the probability of the given grayscale value, the given point belonging to ith cluster, where the ith cluster is represented by your mu I, which is mean I, and variance, that is sigma I square. If you multiply that with the mixing coefficient of that particular cluster and you sum it over all the clusters, you will get the joint probability of this particular point. You have to return the log of this in the joint probability function. So please be careful of applying logs. You will have to apply log in front of this equation. To make it a bit easier, we have also given what log of this the log form of the Gaussian probability of scalar value. So the log form of this probability distribution function for a particular x will look like. You should be using this quite often. You should be needing to use this quite often. And that's pretty much it for likelihood and joint probability. Likelihood is something that you calculate for the model, and it is basically the joint probability for all the points. So you'll calculate the way you did it for a single point, you'll calculate for all the points and sum over, and that should give you the log likelihood. Again, remember, we're asking for the log likelihood. And if we go back here, do you want me to explain all of this again? Because I have gone through it point by point, variable by variable in the last half an hour, and it's recorded, so you can just go back. And if there's something specific that you want me to talk about, you can just tell me here. The equation in the README you mentioned is the same as both the likelihood and 9.25 in the em.pdf. 9.25 is different. 9.25 is calculating your new covariances. The README equation is similar to is this, the log likelihood. So if from the README, if you find it easier, you can refer to that. But 9.25 is different. It's not the same as log likelihood. It's this equation that you're referring to, which is present in README as well. 9.28 is the same as equations in README. Yes, it is evaluating the log likelihood. You can use the same function. So when you're implementing this EM step in your train, you do not have to rewrite or recalculate. There is You don't have to write code for calculating the log likelihood of it again. It is the same log likelihood that you would have implemented in the functions that we've asked you to implement. If you follow the order of initializing, training, and then joint probability, and then likelihood is the same function that you should call here at the end of after implementing the expectation step and maximization step. And okay, anything else before? Let me see if I have covered all the things. Log space, please perform calculations in log space. If you find equations which are not in log space, apply log in front of it, split it in numerator, denominator, and split the terms and then calculate. em.pdf we've discussed. README, I've gone through the README stuff in the folder. It's the main everything that is there in the folder. Feel free to experiment with the images that you have. Um, we encourage you to save your images and see what clusters you're getting, so that you know what you're actually doing, and it's not just about passing the tests and submitting the code to Bonnie. Uh, Clustering and unsupervised learning. Yes, that's pretty much it from my side. I will be here for 5 more minutes in case you guys have any questions here, or I'll be monitoring both YouTube comments and Piazza. Oh, there is one more thing that I think I should mention. The images, the input that is given to you. For grayscale image, it's easy after you flatten the image because you get a one-dimensional array. For the first part, that is k-means, you are given a three-dimensional image. That is, you have the RGB channel. So when you start with means, your means will be um, an array with three values. Like a single mean will be basically 3 points, which is the mean for the red channel, the mean for the green channel, the mean for the blue channel. Uh, so if you want k means, you'll have a matrix of k into three. Just want you guys to visualize it in that way for the k mean section, because we'll be testing your images, because you need to implement your code in um, for colored images for k means. And I hope that helps. Okay, so looks like there are no further questions, and there are no further questions on Piazza as well. So, okay, guys, good luck. We will be holding office hours from the coming week onwards, so just feel free. Piazza will be there always. Ask questions and remember to do your calculations in log space. Be very careful if you get stuck. Try to implement that section again. It can be a little frustrating, this assignment, even if you think you know everything and you think you're doing everything correct, this assignment can be a little frustrating. So take a break and then come back and yeah, do it again. I guess that's the best advice I can give you if you think you are doing everything else correctly. Good luck. Bye. Again, this feels a bit weird saying bye to yourself. I wish you could also see you guys.